Why do I only need 2 legs to stand, but this chair needs 4? This lamp has only 1, but the lamp is different. Its leg is, it's fat. So let's ignore it and focus on skinny legs, like sticks. Let's use sticks to hold this ball up. With 1 leg, it falls. With 2, it still falls. With 3 legs, it stands up. But why 3? Why not just 2? After all, we walk with 2 legs. Here's a thought. Smart people tell us that we live in a 3-dimensional world, so perhaps the concept of dimension has something to do with it. But that word, dimension, what comes to mind when you hear that?
Listen to me!
Spiderman?
I cannot let you open a portal to another dimension. Brooklyn is not zoned.
Do you think of the 4th dimension? Tesseracts? Time travel?
The controls won't work here. We're passing through the bulk. Space beyond our 3 dimensions. All you can do is record and observe.
It's really easy to get sucked into science fiction and pseudoscience if you're not careful.
A dimension of sight. A dimension of mind.
Well, today we will find out what is dimension using linear algebra, and it's going to solve the mystery of why we stand on just 2 legs. How does understanding dimension relate to things standing and falling? Let's go back to our model. To keep this top ball up, we needed the 3 legs to point in different directions. But what does the word different mean? For instance, is this different? The 3 sticks point out with no 2 in the same direction, yet it falls down. So pointing in different directions is not enough. Maybe we should think about sticks a little differently. Let's view our sticks as pointy arrows, or vectors. They point out from the center ball, which we think of as the origin or starting point. To get to this point where my finger is, just go along the red vector a bit, then blue, then yellow. My finger can be here too, it still works. So following these stick directions, forwards and backwards takes you everywhere in our space. So in some sense, these vectors span our space. Span. That's a great word. Instead of saying following these vectors take you everywhere in space, let's just say these vectors span our space. What about these sticks? No matter how you travel along their directions, you can never leave the surface of this table. So they do not span our space. We can now tell apart things that stand up from things that don't. It's a simple relationship. Legs that stand up give vectors that span our space. Of course, the reverse isn't true. Think of the sticks as being part of a pyramid. The 3 sticks themselves don't all lie on the same plane because the base is a triangle and not a line, so they span our space. But as we slide the top point to the right more and more, the solid leans over more and more until it eventually topples over. So while these sticks do span our space, when they are very slanted like this, they will fall down. You can also get new spanning sets from old ones by adding more vectors to it, like this. This is a spanning set because you can still get to every point in space by traveling along the old directions. You don't have to use the new vector. This means that our space can be spanned by more vectors than is needed, but it can't be spanned by too few. This is what makes the first set here special. Take out any vector from it and it no longer spans our space. In other words, the first spanning set is minimal. This is what lets us define dimension. The dimension of our space is simply the size of a minimal spanning set for our space. This makes sense. A minimal spanning set is a minimal set of directions to reach every point in space. So, dimension is just a minimal number of directions to reach every point in space. For instance, these 3 vectors form a minimal spanning set for our space, so our space has dimension 3. With the plane, you can go everywhere following these 2 vectors, so the plane is spanned by 2 vectors and clearly no less. So the plane has dimension 2, the line has dimension 1, a point has dimension 0. In each case, the vectors appearing here form minimal spanning sets for their spaces. Dimension measures how roomy a space is. Why did we talk about it in such a roundabout way using spanning sets? Here's the reason. Spanning sets help connect how we stand to dimension. We already saw that a set of legs standing up gives a spanning set for our space. So, a minimal set of legs gives a minimal spanning set. As a result, a minimal number of legs standing is just the size of a minimal spanning set for our space, which is just the dimension of our space, 3. In plain English, we need at least 3 sticks to stand because we need at least 3 vectors to span our space. This is a beautiful quality that bridges reality and mathematics. The minimal number of sticks needed to stand up equals the dimension of the space you're in. Now you're probably wondering, why do humans only have 2 legs? If we believe 3 is the minimum for standing upright in our universe, why don't we fall down? Weird, isn't it? Just like how we idealize legs as sticks, we should also think about our legs in a more general sense, as appendages, vectors that protrude out of our bodies. You see, in addition to our legs, we also have feet, which are basically stubby little vectors. So a more accurate model for us is this. Voila! It's no surprise that feet help us stand, but here's something people don't really talk about, even textbooks, at least in 2022. Why do our feet point the way they do? Here's what our model tells us. Our feet cannot point sideways. Because if they did, our feet vectors would flare out like this and not span our space, and we would fall down. Okay, if this is how humans stand, why don't stick figures fall down? Look at them, they lack feet. If having these limbs helps us so much, why do people draw stick figures the way they do? Why not add feet? Here's my philosophical answer. Think of where stick figures live. They don't live in our world. They live on paper, on your screen. Their world is the plane. It's 2-dimensional. That's why they only need 2 legs and no feet and still appear stable standing up. Talking about legs raises another interesting question. If having 3 legs is such a stable thing, why don't we see 3-legged animals around? One reason is that almost every animal has an even number of legs. Spiders have 8, many insects have 6, and cats have 4. Well, sometimes 2. Definitely 2 for this guy. An explanation for this evenness is that many animals have inherited a bilateral symmetry from some ancient common ancestor. And so this symmetry must be so baked into our genome that's hard to edit out. Check out the footnote for more explanations. But again, 3 legs. We really want to see 3-legged animals. Can we do that? Actually, let's invent a way to see them. Let's let leg again mean a thing, anything that supports us off the ground. Are there any animals that have a 3rd leg that points out like this? The answer? Yes. That extra leg is the tail. You see, some animals use their tail to support themselves in a tripod stance, like meerkats on the lookout, woodpeckers on a tree, tripod fish, kangaroos sitting, kangaroos fighting, kangaroos on all 5. Okay, this last one's not a tripod, but you get the idea. By thinking about our legs differently, we have discovered a fundamental reason for how we stand. And the key to that, and what I think math does well with, is clarifying the meaning of things, like legs and dimension. There are many more reasons for why we stand the way we do. Our feet. Our heels are kind of big. Our muscles help us balance. Our knees lock. Our glute muscles counteract our forward tilt. That's right, big butts keep us up. What's amazing is how these sciences all work together to explain such a simple phenomenon. Thanks for watching.